On December 27, 2004, a dead star 50,000 light-years away cracked, and in the first 0.2 seconds, it released more energy than our Sun puts out in 250,000 years. That radiation crossed half the galaxy, hit Earth, and disrupted our ionosphere. And that was a quiet magnetar on a normal day. That event wasn't a supernova. It wasn't a gamma-ray burst. It was a starquake, a crack in the crust of a neutron star with a magnetic field so extreme it has its own category in astrophysics. We call them magnetars, and they sit at the absolute limit of what matter and energy can do in this universe. We've covered neutron stars before, city-sized, incomprehensibly dense, where a single teaspoon of material outweighs Mount Everest. That already sounds like the end of the road, but magnetars push past all of that, into a regime where the physics we use to describe ordinary matter simply breaks down, where empty space stops being empty, where atoms stop being atoms, and where the energy output of a single event dwarfs anything else we've ever recorded in the observable universe. Neutron stars are already the densest objects with a solid surface in the universe, the ultra-dense corpses left behind when a massive star explodes in the supernova. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's, which is already absurd. But some neutron stars are born spinning insanely fast, 1 full rotation per millisecond. And when that happens, something kicks into overdrive in the first 10 seconds of the star's life. The turbulent, boiling interior acts like a dynamo, converting all that rotational energy into magnetic energy at a rate that makes a regular neutron star look like a toy compass. The end result is a magnetic field of up to 100 trillion Gauss. To put that in perspective, Earth's magnetic field sits at about half a Gauss. The strongest MRI machine in a hospital hits roughly 100,000 Gauss. A magnetar is 1 billion times stronger than that MRI. Now, here's what I love about this. There's a special threshold in physics called the Schwinger limit. It's the point where the magnetic field is so strong, it starts messing with empty space itself. A magnetar doesn't just approach that limit, it blows past it. And that's where things get really weird. But I'm getting ahead of myself. Let's talk about what this field actually does first.
A hydrogen atom is a sphere, 1 proton, 1 electron, held in a round cloud by the electrical attraction between them. That spherical shape is the foundation of all chemistry. Every molecular bond, every protein, every cell in your body depends on electrons occupying that geometry. Near a magnetar, the magnetic force overwhelms that electrical attraction entirely. Electrons get crushed down into what physicists call Landau levels, the lowest possible energy state, and the atom stops being a sphere. It becomes a needle, a long, impossibly thin filament of matter compressed to about 200 times narrower than normal. These needle atoms can then stack end to end, forming long magnetic polymers, chains of matter that have no equivalent anywhere else in the universe. The consequence is straightforward and total. Chemistry stops working. Molecular bonds require electrons in specific shapes and positions that simply no longer exist in that environment. There are no molecules on a magnetar surface, no compounds, no reactions. The concept of a solid object becomes physically meaningless. We're not talking about extreme conditions that stress ordinary matter. We're talking about a regime where ordinary matter as a category ceases to exist. Physicists are still writing the equations to describe what replaces it.
Here's where the physics gets genuinely strange, not just extreme, but structurally different from anything we deal with on Earth. At the quantum level, empty space is never truly empty. It constantly fluctuates with what physicists call virtual particle pairs, matter and antimatter partners that pop in and out of existence in fractions of a second, everywhere, all the time. Under normal conditions, this is irrelevant background noise. But once a magnetar's field crosses a threshold called the Schwinger limit, it becomes strong enough to influence those virtual particles directly. The vacuum gets polarized, and polarized space stops behaving like nothing. It behaves like a crystal. Light, which always travels at the same speed regardless of direction, starts moving at different speeds depending on how its electric field is oriented relative to the magnetic field. This effect is called vacuum birefringence, and it's a prediction of quantum electrodynamics that physicists had been trying to confirm for decades. In 2024 and 2025, NASA's IXPE telescope detected X-rays from magnetars with polarization levels reaching 80%, a result that only makes sense if the magnetized vacuum is real and actively shaping the light passing through it. And it goes further than that. Some photons near the magnetar surface don't just change speed, they split. A single gamma-ray photon traveling through the magnetized vacuum spontaneously becomes two photons. This is called photon splitting, and it is flatly forbidden in classical electrodynamics. It happens here because the nonlinear quantum structure of the vacuum makes it possible. The rules of electromagnetism don't break, they get replaced by a more complex version that only activates at these field strengths.
December 27, 2004. SGR 1806-20. A magnetar sitting 50,000 light-years away in the constellation Sagittarius experienced a starquake, a fracture in its iron crust caused by the buildup of magnetic stress that had finally exceeded what the solid lattice could hold. The magnitude of that event would register at roughly 32 on the Richter scale. The most powerful earthquake ever recorded on Earth was a 9.5. In the first 0.2 seconds of that crack, SGR 1806-20 released more energy than our Sun produces in 250,000 years. That radiation crossed 50,000 light-years and was still powerful enough to disturb Earth's ionosphere, blind gamma-ray detectors on multiple satellites, and saturate instruments that weren't designed to have an upper limit for something this close. Had SGR 1806-20 been within 10 light-years of Earth, that single flare would have stripped the ozone layer, triggered a mass extinction, and irradiated the entire hemisphere facing it at levels comparable to a nuclear detonation across the whole surface. The nearest known magnetar is 9,000 light-years away, far enough that we're not in danger. But the 2004 event is a useful reminder that safe distance is doing a lot of work in that sentence.
For years, fast radio bursts were one of the most frustrating mysteries in astrophysics. Millisecond-long flashes of radio energy with brightness temperatures hitting 10 to the 36 Kelvin, arriving from across the universe with no clear source. In 2020, a magnetar in our own galaxy, SGR J1935+2154, produced one we could actually trace back. That settled the core question. Magnetars are the engines. A starquake jolts the magnetic field, drives waves through the surrounding plasma, and launches a coherent burst of radio energy intense enough to be detected across billions of light-years. What's less settled is the energy budget. By 2024-2025, one repeating FRB source was firing at 729 bursts per hour at peak activity, a rate that strains the standard magnetar model considerably. One leading explanation involves a binary companion, a star whose ejected plasma periodically interacts with the magnetar and triggers new bursts. The 2024 detection of sudden rotation measure flares from FRB 220529A is consistent with exactly that scenario. On the same object that produced the 2004 flare, SGR 1806-20, researchers proposed in 2024 the existence of a planetary companion, a rocky body between 10 and 18 Earth masses, orbiting on an eccentricity of 0.994. If confirmed, it would be the most magnetically exposed planetary object ever identified, and it would raise serious questions about how planetary systems survive the supernova events that produce magnetars in the first place. At the core, the physics becomes genuinely unresolved. Under pressures several times nuclear density, protons and neutrons may dissolve into a deconfined sea of quarks and gluons, the same state of matter that existed in the first microseconds after the Big Bang. The equations of general relativity and quantum chromodynamics don't converge cleanly at those densities. Different models predict different interiors, and we currently have no observational tool precise enough to distinguish between them. A magnetar is a dead star, smaller than a city, with a magnetic field strong enough to reshape atoms, polarize the vacuum of space, split photons in two, and disturb Earth's ionosphere from 50,000 light-years away. Its chemistry is unlike anything that exists elsewhere. Its core may be in a state of matter that our best equations can't fully describe. And we estimate there are over 30 million of them drifting inactive through the Milky Way right now, Former monsters, gone quiet, undetectable. That number alone is worth sitting with for a moment. If you want to go deeper on any of this, the gravitational wave signatures of starquakes, the full picture on vacuum Birefringence, or what the FRB energy crisis actually means for the Magnetar model, let me know in the comments. And if someone you know would get something out of this, send it their way. Take care, and I'll see you in the next one.